Alright, let's begin with the second part of section 2.4. So we're going to look at another example continued from last time, where we need to complete a table and use that result to estimate the limit. Then we'll use our graphing calculator to graph it to confirm our result, and then we'll figure out what the limit value is, etc. So go to y equals, and remember that the top needs parentheses for order of operations. If you have a newer operating system, your calculator will probably show it to you in a better way. Mine's an old one. I like it that way. So go to the table, and you can delete the old values by pushing the delete button and start plugging in these numbers. Oh, I need a negative 3.01. I typed in the same thing. And a negative 3.001. Boy, there we go. So these are this we're looking at the limit as x approaches negative 3. So it's negative 5.1, negative 5.01, negative 5.001. Now we can try going from negative 2.9, negative 2.99, and then negative 2.999. So look for a pattern. There's always going to be one, and we need to figure out what that is. The pattern is the y value is approaching negative 5. So you'd say L is negative 5. We're going to push graph and see what that looks like. A line again. We'll have to get to the bottom of that in this section. So why are we graphing rational functions excuse me, and getting lines at the end? If I push trace and type in negative 3, once again y is undefined, but let's try negative 3.001 and it's somewhere there. So it's close to negative 5. So when I copy this graph over, I need to have some amount of accuracy. There's negative 3, negative 5. There'll be a hole there. Then I'm going to type in 0 to get one more point, which is negative 2. So the line goes like so, and there is the graph. The calculator does not give the open hole, but it's our job to put that in. Now, for the rest of this section, we're going to be doing limits algebraically. And what that means is we'll be using some techniques to calculate what the y value is. This is your y. As x approaches negative 1, that's a minus. My arrow is hitting the minus sign. And we need to figure out what the y value approaches. Some of these problems that are polynomials, it's pretty straightforward. We just substitute in negative 1. So I'd say this limit equals negative 2 times negative 1 squared plus 3 times negative 1 minus 5. Order of operations, do the exponents first. That's just a 1, minus 3 minus 5. Negative 2 minus 3 minus 5. I'm getting a negative 10. Notice how I drop this limit notation when I actually plug in for x. Okay, so I don't write LIM anymore. I'll draw a line here. For the next question, B, the same way, we're going to substitute the 3 there. I'm not going to write limit anymore, just plug in. This is equal to 3 plus 6, which is the square root of 9, which is just 3. So 3 is the limit. This next one should look familiar to you. It's the very first problem, the one that we did up here. So how do we do it algebraically? If I were to plug in negative 3 for x, I would get 9, because negative 3 squared is 9, minus 3 minus 6. On the bottom I have negative 3 plus 3. So that's 9 minus 3 is 6. 6 minus 6 is 0 over 0. Now 0 on top is 0. 0 on bottom is undefined. But 0 over 0 is something that is, we have not seen it before. What it really means is that it could be any number. It just depends upon what x is doing. So what we need to do, if you see 0 over 0, that means we need to investigate. We need to do more work. It does not mean undefined necessarily. It does not mean 0. It means it could be half. It could be negative 5. It could be 2. We'll get to the bottom of this by doing some algebra. So the top actually factors. Do a little reverse FOIL. Notice how here I'm connecting my steps, and since I'm actually not plugging in negative 3, I'm writing LIM. I'm carrying all that down. And then I'm going to factor. It's going to be x plus 3, x minus 2 divided by x plus 3. Now if you do this correctly, you'll always have something that's going to be common. This was what was causing the 0 over 0. When I plug in -3 here, that becomes a 0 and that becomes a 0. But now that we've cancelled it out, we can go ahead and plug in -3, which means I won't write this LIM. I'll just go -3 minus 2, which equals -5. And this is the final answer. And hey, it does match how we got it here using the table and how we got it using the graphing calculator. Alright, so there's going to be a few practice problems in your homework where you'll have to factor and reduce. The next one, if I plug in 9, the square root of 9 minus 3 over 9 minus 9, this is 3. So you get 3 minus 3, 0 over 0. 0 over 0 doesn't mean the end of the road. It means we need to investigate further. So earlier when we reviewed, we noticed that when you have radicals, you can rationalize. So we're going to actually rationalize the numerator. So you have root x plus 3. Leave this x minus 9 exposed and have root x plus 3. So we use the conjugate. The top you're going to multiply because you want to multiply the conjugates. So root x times root x is x. The outer and the inner cancel. Now do the last. You have x minus 9. Leave these as they are, and then you'll notice which two bad factors were causing the 0 over 0. This x minus 9. When you plugged in 9, that was causing the issues, but we can get rid of it. You have a 1 left on the top. Now we can plug in the 9. So it's 1 divided by square root of 9 plus 3. That's 3 plus 3, so it's 1/6. Once again, notice how I wrote limit until I had x's. I wrote the LIM, and then when I actually plugged in for x, I dropped the limit notation. So you may have to do some other kinds of algebra in the future. If you get a 0 over 0, you may need to do a common denominator or any other things that we have reviewed to clean up so that you actually can find the limit. Okay, the next few questions involve a little bit of different kind of thinking. So we can go back to our notes real quick. These limits, E, F, and G, notice that x is approaching infinity there. So this is called the long-term behavior. So section 2.4, limits involving infinity. So if you have the limit as x goes to infinity of 1 over x, let's use number sense and try to see what happens. As you know, infinity refers to numbers getting large beyond bound. So take a look at, supposing you do 1 over 10. 10's not that big a number, but notice how you get 0.1. What happens as you increase the size of the number in the bottom? Your output gets smaller and smaller. 1 divided by 1,000 is 0.001. 1 divided by, let's do a bunch of zeros. This E minus 5 really means it's 0.00001. 0.00001. It's 4 zeros. Okay, it's a pretty small number. So what this is telling me is that the limit, though it's a limiting value, what is this approaching as x gets big? And the answer is 0, because our values are getting smaller and smaller. Now if the limit of 1 over x as x goes to negative infinity is pretty much the same thing. Because if you have 1 divided by negative 10, 1 divided by negative 1,000 or 10,000, it's going to be negative 0.0001, which is still getting close to 0. Okay, so basically 1 over a large number goes to 0. That's what we're saying here. Okay, so to do problems where you have more terms, like let's say you have the limit as x goes to infinity of x minus 1 over 2x plus 3. What you want to do here is look at what actually plays a role. When x gets really big, this minus 1 and this plus 3 are just constants. They're not going to play that huge a role. One way to think about it is, think of a really, really wealthy baseball player, the huge $1 million contract, $30 million contract. Would it hurt them if you take away $3 from them? No. Would it hurt them if you took away $1 from them? No. So what really matters is these leading terms. So you're going to take this limit and write it as a new limit as x goes to infinity. This limit is equivalent to x over 2x. Notice we're not canceling, that's illegal. We're just writing it as a new limit. And now you can cancel the x's and you just get half. There is no limit anymore, the x's went away. Okay, now to actually justify this reasoning, we're going to go to y equals, and on the top I'm going to write x minus 1 divided by 2x plus 3, and go to the table and delete all this. X gets big, so it's 10, try 100, 1000, well actually that was too many zeros. What do you notice? To the y column, y is getting pretty close to 0.5, which is the 1/2. Notice how quickly we were able to get it, whereas here we need to put a few more zeros to be certain, and eventually we'll get there. Now this is the first case, case 1, where the degree of the top and bottom were equal. The second case is if you have the limit as x goes to 0, and let's say you have 2x divided by x squared plus 5. Here the degree on top is less than the bottom, and once again the same baseball player analogy, we can drop $5, won't hurt, just look at the leading terms. And here the x cancels with one of these x's, so you have the limit as x goes to infinity, 2 over x. 2 divided by a large number, that limit is 0. Okay, so the degree of the top is less than the bottom. This dominates, gets bigger, get a 0 as x goes to infinity. Case 3, well, what's case 3 going to be? The degree here was the same, 1 and 1, smaller than the bottom. So now it's a reverse. Let's say you have x squared plus 5 on the top and 2x on the bottom. We'll continue with the same logic. We'll drop the $5, okay, and write it this way. But this time when you reduce your fraction, you have an x on the top and just a 2 on the bottom. So here you have x getting really big divided by 2, it's still really big. So this limit, when you have a bigger power on top, it dominates, or you can say it does not exist. Back to the worksheet now. There's 3 questions coming our way. So here, E, limit as x goes to infinity. Well, this is small change, small change, small change, small change. Even though there's an x, you only focus on the leading terms. Everything else is small change. And once you do this, the x squares can cancel, and you just get 2/5. You can verify it by using the calculator. I won't be doing it again on this one, but feel free to pause the video and do it. Notice how when the degree of the top and bottom are equal, the final limit is just the leading coefficients. You have learned this before when you studied something called a horizontal asymptote back in a previous algebra class. You can check your notes on this. That's the concept. Okay, next one, the degree of the top is bigger than the bottom, so that's going to dominate. But to show our work, I'm going to get rid of the small change, look at only the leading terms, 3x squared over 2x. Here the x's cancel, leaving you with an x on the top, and just a 2 on the bottom, so it's negative infinity times 3/2. It goes off to negative infinity, or you can say does not exist, because that's not a real number. Okay, one more. The degree here is smaller on top, larger on bottom. Once again, look at only the leading terms, keep the 3, drop that, just look at 2x. So it's basically 3 over a large number, goes to 0. Now sometimes students get into a role and do these problems, and then they say, oh, the degree is the same, the answer is 3/2. But this is a trap. I put it in there intentionally. X is not approaching infinity, it's approaching 1. So just plug in 1, 3 times 1 squared plus 5 over 2 times 1 squared minus 1. That's 8 over 1. The limit is actually 8. Okay, so this ends to 4. Be sure to try the homework. Send me questions from WebAssign if you have any.